Assalamualaikum warahmatullahi wabarakatuh, and good day, guys. Alright, so now we enter for the part 2 of the gas power cycle for the KJM 442. So in this part, basically, we will focus on the example and exercise that related to the gas turbine engine. So now we enter for the chapter 3, part 2. So in the part 1, you already learned about the basic principle, the components, the calculation, and also the performance. Now we come to the actual performance calculation for the gas power cycle. Alright, for this example 3.1, so the ideal A standard Brayton cycle operate with the air entering the compressor at 95 kilopascal, 22 degrees Celsius. So that means you can see here it already stated that, the air entering the compressor at 95 kilopascal, 22 degrees Celsius. So that means this one is at here, entering the compressor. The pressure ratio RP is 6, okay, and the air leave the heat addition process at 110 Kelvin. So that means 110 Kelvin is a temperature that leaves the heat addition process, which is at T3. So addition is from 2 to 3. So that means the T3 is 1100. So you have to calculate the compressor work, the turbine work, the cycle efficiency, and back work ratio. Okay, so now we try to solve this. Okay, the first one, when you're dealing with the Brayton cycle case, or Otto cycle case, or diesel cycle case, or maybe after this you will experience for the Carnot cycle, refrigeration cycle. So the first one, you have to develop your TS diagram or PV diagram, because the TS diagram and PV diagram will give indication, okay, how the level of your understanding about this problem. So you start with your solution, okay, with the TS diagram. Okay, so the TS diagram is here. Okay, so the TS diagram. So state 1 to state 2, state 3 to state 4 is something like this one. Okay, 1, 2, 3, 4. In this case, they give you the value of the P1. So P1 is given, which is in this case 95 kilopascal. Okay, the equation 95 kilopascal, and then they give you the value of T1, which is in this case is 22 degrees Celsius, which is you have to convert into Kelvin. So we have 295 Kelvin. Okay, right, 295 Kelvin. And then they give you the value of RP. So RP is a ratio between P2 and P1. Okay, equal to 6, right? And then they give you temperature after leaving the heat addition process, which is T3. So T3 1100 degree Celsius, or 1100 Kelvin, right? So 100 Kelvin. Okay. Okay, alright. Okay. So I just give the suggestion to all of you. So when you're dealing with this kind of a problem, so you need is very advisable to all of you to calculate each state. So find all the parameter at each state. So start with state 1. Okay. State 1 doesn't need to calculate because it's already given in the equation. P1 is equal to 95 kilopascal. Okay. And then they give you the value of T1, which is 295 Kelvin. So settle for the state 1. And then we'll go for the state 2. Okay. At the state 2, is a process of the isentropic compression, right? So you can use the isentropic relationship, which is in this case is T2 over T1 equal to P2 over P1 powered by K minus 1 divided by K. So this one actually is equal to RP K minus 1 divided by K. So you can calculate T2. So T1 is given 295, okay, and RP is given 6 powered by 1.4 minus 1 divided by 1.4. So from here, the T2, you will get 492.21. You will get 492.21 Kelvin. So there's a value of T2. And then you go for the state 3. Okay, state 3. State 3 is a constant pressure heat addition. Okay, right. Heat addition. Oh, sorry, I use the red mark because I think it's more clear. Okay, I'm sorry. So hopefully it's okay for you. So T3 is given. T3 is equal to 1100 Kelvin. Okay, settle. And then you can start with the state 4. Okay, you can go for the state 4. Okay, for the state 4. Okay, state 4 is a process of isentropic expansion. Okay, so you can use isentropic relationship, which is T3 over T4 equal to P3 over P4. Okay, powered by K minus 1 divided by K. Okay, so you know that the P3 equal to you refer to the PV diagram. So PV diagram, so something like this one. Okay, 1, 2, 3, 4. So P3 equal to P2 and P4 equal to P1. So from here, you will get this one is equal to Rp powered by K minus 1 divided by K. So T4 actually is equal to T3. So T3 1100 divided by the 6 powered by 1.4 minus 1 divided by 1.4. Then you get the value of T4 is equal to 695, okay, 0.2. Okay, right, Kelvin. Okay, boleh kira. So you can get the value of T4. Then you already got all the temperature at each state. So now the first question is you have to calculate the value of compressor work. Compressor work. So compressor work can be determined by process of mass flow rate Cp T2 minus T1 because you know that at here the process at the compressor and here you know that process at the turbine and here which the Q in is occurred and here is Q out. The first question is compressor work. So since mass flow is not given, so it's equal to Cp 2 minus T1. So put the values 1.005. So T2 calculated is 492.21. T1 is 295. And then from here, you will get the value of the compressor work is 198.196. Okay. Yes. Alright. Okay, clear? Okay, so that's what I'll do. Compressor. Alright. So the second question is you need to calculate the W turbine. The W turbine is occurred at between state 3 and state 4. So that means the mass flow rate you kalikan dengan Cp T3 minus T4. So mass flow is not given. So just simply T3 minus T4. So put the values. So here is 1.005. T3 is 1100. T4 is 659. Okay. 659.2. Okay. 27 basically. 27. So here is 27. Okay. So you get eventually we get the value of W turbine is equal to 442.93. Okay, kilojoule per kg. Okay, clear. Okay. So you just simply get the value of W compressor and W turbine. Okay, and then the next question, okay, the next question, they ask you about the, so you solve for the, you solve for question A and question B. Then question C, the cycle efficiency, so thermal efficiency. So the thermal efficiency, the formulation is W net over Q in. So W net can be determined by W turbine minus W compressor. So W turbine actually is 442.93. Okay, 442.93 minus W compressor is 198.196. Okay, right. So you will get, so here is 93.937. Okay, so W net you get is 244. Okay, 244.7376. Okay, so you can calculate this one. Check. Okay, right. So you get the value of W net, and then the value of Q in is m dot Cp, because Q in is occurred between state 2 and state 3. So that means here is T3 minus T2. Since the value of mass flow is not given, so you can simplify this equation. Okay, so you can start put the values 1.005, T3 is 1100, T2 actually is equal to 492.21. Okay, right? So you get the value of Q in is equal to 610.8284. Okay. Okay, clear. Right. So you got the Q in, and then the thermal efficiency can be calculated. Okay. So 244.7376 divided by 610.8284. The thermal efficiency is 0.4. Okay. Right. Then the last question is, you want to calculate, this one is question number 3, sorry. Okay. Number 4 is the back work ratio. So you just simply divide the W compressor and W turbine. In this case, W compressor is 198.196 divided by 442.933. So you get the back work ratio is 0.447, if not mistaken. Okay, clear? So this is typically the question, right? So the first, you have to identify the parameter, okay, which state that they are given, and at the same time, you have to develop your TS diagram, and then you have to do state by state. And then after that, it's easily to calculate all the calculation. State 1, state 2, state 3, state 4. And then you can calculate W compressor, W turbine, thermal efficiency, back work ratio, right? So it's very easy. Okay. Alright, it's okay. Now proceed to example 3.2. So in the gas turbine unit, air is drawn at 1.0 bars and 15 degrees Celsius and is compressed to 6.2 bars. The maximum cycle temperature is limited to 800 degrees Celsius. So that means the compressor work, turbine work, cycle efficiency, and back work ratio. So in this case, they give you is drawn at the 1.2 bars and 15 degrees Celsius. So this is going to be conditioned at state 1. After that is compressed, man. That means you can expect that it enter the compressor to 6.2 bars. So this is going to be state 2. Okay, because process 1 to 2 is processed at the compressor. So the pressure is increased from 1.02 bars to 6.1 bars. Okay? And then the maximum cycle temperature is 800. So the maximum cycle temperature is, if you look into the TS diagram, okay, if you look into the TS diagram, okay, 1, 2, 3, 4. So the maximum one is a 3, right? The highest. So this one is going to be P3. Okay. Then, okay, you have to calculate all this term. Okay. Right. So example 3.2. Okay. As I mentioned earlier, if you want to calculate related to the Brayton cycle or any cycle in the thermodynamics, so you start with the TS diagram. You start with the TS diagram. So here, consider this one. So 1, 2, 3, 4. So the condition is given, basically the P1 is given, okay, 1.02 bars. So this one you have to convert into kilopascal, which is 102 kilopascal, because 1 bar is equal to 100 kilopascal. And T1 is given, so T1 actually is equal to 50 degrees Celsius. So in this case, 50 degrees Celsius is 288 Kelvin. 288 Kelvin. Okay, clear? And then also give you the value of P2. So P2 is equal to 6.12 bars. So 6.12 bar. So that means this one is going to be 612 kilo Pascal. Okay. And then they give you the value of T maximum. So T maximum is equal to T3. Yeah? So T3 is equal to 800 degrees Celsius. When you convert into Kelvin, there will be 1073 Kelvin. Okay, clear. Right. And then at the same time, you know the P2 and P1, so you can calculate the value of RP. So never mind. Okay. So similarly like previously, you have to do state by state. Start with state 1. So state 1, P1 is equal to 102 kilopascal, and P1 also given by 288 Kelvin. Okay. Okay, clear. Right. So no problem. You go for the state 2. State 2 is a process of isentropic compression. Okay, compression. So, isentropic compression, that means you can use isentropic relationship. T2 over T1 equal to T2 over P1, K minus 1 divided by K. So, in this case, so T2, so T1 is equal to 288. So, P2 is equal to 612. This one is 102. Powered by 1.4 minus 1 divided by 1.4. Then you will get the value of T2 actually is equal to, I already calculated, so 480.531. 480.531 Kelvin. Okay, right? And then you go for the state 3. It's a constant pressure, heat addition. So T3 basically is equal to T maximum, which is in this case is 1073 Kelvin. Okay, settle. So and then you go for the state 4. You go for the state 4, the process of isentropy, expansion. Okay, expansion. So we have here is T 4 over T3. Okay. Sorry. Okay, this one it's okay if you want to do T4 over T3. That means P4 over P3. Yeah. Okay, but we just follow last example. T3 over T4 equal to P3 over P4. Okay, K minus 1 divided by K. So since P3 equal to P2, P4 equal to P1. So how you get this? You refer to the PV diagram. So PV diagram. So something like this one. Okay. Ni 1, 2, 3, 4. So here is P2 equal to P3. Here is P4 equal to P1. Okay, right. So you can find the value of T4. So T4 is equal to T3 is 1073 divided by P2 over P1. So P2 is 612 divided by 102 powered by 1.4 divided minus 1, 1.4. Then the value of T4 actually is gain 643.089. Okay. So they are all the properties, and then you can start answering the question. The first question is W compressor, if I'm not mistaken. Okay, so W compressor is the mass flow rate carried by Cp T2 minus T1, because you know that this process is at the compressor, this process at turbine, and this one is Q in. Okay, so since the mass flow is not given, so you can simplify by Cp T2 minus T1. So Cp actually is equal to 1.005. T2 actually is equal to 480.531 minus T1. So T1 is 288. So basically you will get the value of W compressor is equal to 193.49. Okay, clear? And then question number 2, you can calculate the value of W turbine as per required, which is M dot Cp, so T3 minus T4. Okay, and then since mass flow is not given, so it's just Cp T3 minus T4. So here is 1.005. T3 actually is equal to 1073 minus T4 is 643.089. Okay, and then the last one we got W turbine actually is equal to 432.061. 432.061. Okay, clear. So you got W compressor and W turbine. Now question number 3, this question asks you about the thermal efficiency. So thermal efficiency is W net over Q in. So W net actually is equal to, W net is equal to W turbine minus W compressor. So W turbine actually is equal to 432.061. Okay, 432.061 minus W compressor. So W compressor is 193.49. Then you get the value of W net actually is equal to 238.5673. 238.5673. Okay, right. Okay, right. And then the value of Q in is M dot Cp T3 minus T2. So since the value of mass flow rate is not given, so you can simplify by Cp T3 minus T2. This one is 1.005. T3 is 1. T3 is equal to 1073. Okay. T2 is equal to 480. 480.531. Okay. now the value of Q in actually is equal to 595, okay? 595.4313, 4313, okay, kilojoule per kg, right? And then the thermal efficiency basically is get the value of 0.4, okay, right? Then for the last question, so number 4, it required you to calculate backward ratio, okay? So backward ratio is just simply W compressor divided by W turbine, okay? W compressor basically is equal to 193.49, okay? 193.49. And then the W turbine basically is equal to 432.061, okay? Then you get the value of backward ratio is equal to 0.447. Okay, okay. So we can check the values, okay? So far we have done 3 examples, okay? So the method is similar. You do state by state, find out the temperature first at each state, then after that you can proceed to calculate the to answer the question. Okay, now you go for the example 3.3. So air enter the compressor of gas turbine at 100 kilopascal and 25 degrees Celsius. So this one basically is the condition at state 1. And then they give you the mass flow, which is 6 kilogram per second. For the pressure ratio of 5, so they give you RP equal to 5 and maximum temperature of 850 degrees Celsius. You will determine the backward ratio, thermal efficiency, and net power developed. So, similarly, okay, like before, so you start with your TS diagram first. Start with your TS diagram. Here is TS diagram. So, something like this one. Okay, so 1, 2, 3, 4. Okay, so basically they give you the value at the first one. They give you P1. Okay, so P1 actually is equal to 100 kilopascal. Okay, and T1 is given by 25 degrees Celsius. Basically, this one is equal to 298 Kelvin. 298 Kelvin. Okay, clear? And then they give you the value of the mass flow rate. So mass flow rate is 6 kilogram per second. Okay, and then they give you the value of the RP, so the pressure ratio. So RP is equal to P2 over P1 equal to 5. And then they also give you the value of T maximum, which is 850, if I'm not mistaken. So 850. So T maximum, so T3 lah. So T maximum, which is 850 degrees Celsius, or this one is equal to 1123 Kelvin. Okay, clear? So now you have to do state by state. We start with state 1. Okay, state 1. So P1 actually is equal to 100 kilopascal, and T1 is equal to 298 Kelvin. Okay, right? And then you go for the state 2. So for the state 2, it's isentropic compression. Okay, isentropic compression. You can use isentropic relationship. So T2 over T1 equal to P2 over P1. K minus 1 divided by K. Also this one is equal to RP. K minus 1 divided by K. So T2 actually is equal to T1. So T1 is 298. Okay. Then RP is given by 5. 1.4 minus 1 divided by 1.4. And you get the value of T2 is equal to 471.978. 471.978. Okay, Kelvin. And then you go for the state 3. State 3 is a constant pressure. heat addition. Okay, basically this one is T max. Okay, T3 is equal to 1123 Kelvin. Alright. Okay. Okay, so right there. So then you can go for the last state, which is state 4. Okay, state 4, acentropic expansion. Okay, clear. So you can use acentropic relationship, which is T3 over T4 equal to P3 over P4, K minus 1 divided by K. This one is equal to P2 over P1, K minus 1 divided by K. And this one also equal to RP, K minus 1 divided by K. And then the value of T4 is equal to T3. So T3 is equal to 1123 divided by RP. So RP is equal to 5. Okay. 1.4 minus 1 divided by 1.4. So eventually you get the value of T4 here is equal to 762. Sorry, not 762, sorry. Okay, not 762. And then T4 actually you will get 677, okay, 4761 Kelvin. Okay, clear. And now you go for the first question, back work ratio. So back work ratio basically is just simply W compressor divided by W turbine. Okay, so W compressor basically is equal to M dot Cp T2 minus T1. So the mass flow rate is given by 6. Okay, so 1.005. T3, T2 is equal to 471.978 minus T1. T1 is 298. So now you get the value of W compressor is equal to 1049. 1049.1 kilojoule per kg. Okay, clear? And then you have to calculate also the value of W turbine. So W turbine is equal to M dot Cp T3 minus T4, because you know that the turbine process occur between state 3 and state 4. So get the value. So 6, 1.005. T3 actually is equal to 1123. Okay. T4 is equal to 677.4761. Then you get the value of W turbine actually is equal to 2358. Yeah? Okay, 2385, sorry, 85 kilojoule per kg. And then the back work ratio you can calculate, which is 1049.1 divided by 2385. Then you get the value of back work ratio actually is equal to 0.44. Okay, right. Then question number 2, okay, is a question about the thermal efficiency. So thermal efficiency is equal to W net over QE. So W net can be calculated by W turbine minus W compressor. W turbine basically is equal to 2713, okay, 2713.166 minus W compressor is 1049, so 1049.1, okay. So we have here actually W net is equal to 1664.077. Okay, right. And then the value of Q in you have to calculate by m dot cp T3 minus T2. So mass flow rate is given 6. CP is 1.05. So T3 actually is equal to 1123. Okay. T2 is 471.978. So from here you can get the value of Q in, which is Q in is 3624. Okay. 0.161. Oh, sorry. The unit here is actually not right here. So yeah. So because they give you the value of mass flow rate, so that means the unit will be kilowatt. Sorry. Okay. Please correct it. The previous one also the unit. The unit here basically is kilowatt. Unit is kilowatt. Sorry guys. So kilowatt. So here is kilowatt. Kilowatt and then kilowatt. Okay. So you got the W net and Q in, then you can proceed to calculate thermal efficiency, which is 1664.077 divided by 3624.161. So here you get the value of thermal efficiency is 0.369. 369. And then the last one, you have to calculate the W net. So W net is okay. So W net, network output, W net is W turbine minus W compressor. You'll be calculate here. So you have 1664.077 kilowatt. Okay, right. Okay, right. Okay, I think that's all. Okay, right. Okay, so anything if you want to check, please check if I afraid I do some mistakes, so please check. Okay, the calculation. So I think that's all. Okay, for the part 2 of this gas power cycle for part 2. So I hope you understand all the example that has been given. I do step by step, so you can follow this step, or maybe you can find any much easier for you. It's up to you, as long as you produce the correct final answer. Okay, guys. Until now, so I think that's all for part 2. So see you on part 3 of the gas power cycle, chapter 3. So on the part 3, you will learn about the actual cycle for the gas power cycle. Okay, see you guys. Thank you very much.